So it's my pleasure again to introduce our next speaker, Dr. Robert Jacobson. Rob is the branch chief of the River Studies branch of the U.S. Geological Survey here in town in Columbia, Missouri. As many of you know, he's been studying our floodplains and flooding events over the years, and today he's going to talk to us about floodplains, flood mitigation, and ecosystem services. Dr. Jacobson.
Thank you very much, Shibu. It was great to be here. I'm glad to have a chance to talk about this topic in this session. I am going to bring in some agroforestry as part of this, or the ecosystem services comes in. I'd like to acknowledge my co-author, Garth Linder, who's with the Geography and Environmental Systems Department at the University of Maryland, Baltimore County, who's done some of the modeling results I'm going to show you. So what's the motivation for this work? People have been involved in working on river restoration, especially in large rivers like the Missouri and Mississippi, for a long time, and they've been concerned about restoration of floodplains. But nothing gets people more interested than big floods. And so in 2011, we had the big flood of the Missouri River, which caused a lot of floodplain damage, and that's what really got people's attention. So our motivation is this devastating flood in 2011, and previous ones, 1995, 1993, et cetera, making us think that there might be some common ground that can be explored between restoration and flood risk reduction. The idea is that if flow corridors can be defined and implemented on large rivers, there might be an opportunity to increase resilience, increase the ecosystem services, while still maintaining revenue for the private landowners. This is not a new idea. The authorizing legislation for most of what's happened in the Missouri River is the Flood Control Act of 1944, and when this was being discussed, there was a report that came from Colonel Pick with the Corps of Engineers, where he described the flow corridors that should be implemented between Sioux City and St. Louis. Starting with this statement: complete protection against all floods of record by levees alone is impractical. Very prescient, very basic sort of understanding of hydrology. And he suggested that there should be a 3,000-foot minimum from Sioux City to Kansas City and a 5,000-foot from Kansas City to Missouri to the mouth at St. Louis. What's interesting about this is that it never got implemented. I'm not sure if it ended up in the authorization or what the actual point was. Maybe it's because there's a legacy of a century of levee building before the 1944 Flood Control Act. But this flow corridor was not implemented. And currently there are areas that have as little as 800 feet between the levees along the lower Missouri River. After the flood of 2011, this idea came back. This is a quote from General McMahon, who was the commander of the Northwestern Division at that point. So this is the Army Corps of Engineers, known for its structural changes, structural solutions, saying we need to do something non-structural, acknowledging that there is a role for floodways, flow corridors, changing existing levee alignments or setting back levees to allow more room for the river. In a way, this is a way for the Corps of Engineers to get people off its back, because they basically say that we're not totally responsible for flood risk reduction, flood mitigation. There's some local things that should be done and can be done as well. So our objective in our research is to explore some of these ideas, try to understand the trade-offs and commonalities between restoration and flood risk reduction on a highly managed river system, exploring the sensitivity to relevant geometry, different levee setbacks, and land use scenarios. So those two things are floodway designs, what do those levee setbacks look like, but also what sort of land use would take place within that flow corridor, which is where the connection to forestry, trees, and agroforestry takes place. And we're going to evaluate stage reduction, flood attenuation, things we would consider to be things that are related to flood risk reduction, as well as how those might affect ecosystem benefits generated within those flow corridor areas. We are in exploratory phase, and so you see that things like quantifying ecosystem benefits, We have an approach to that, but we don't obviously have it solved yet. What I'm going to describe today is some multidimensional hydraulic modeling we've used to evaluate water levels, flow velocities, water residence time, and complexity of flow of the floodplain. Essentially, we're saying this physical part of the system is what's driving eventually the biotic responses and any economic and socioeconomic responses as well. But we want to get the physical part right first as the foundation for this. This provides us the ability to explore a wide range of sensitivity to alternative floodway scenarios, land uses, and associated hydraulic roughness. Hydraulic roughness is a very important thing, as you'll see. We're using a simplified representation of hydraulic resistance to model these effects, so we can say, okay, well, different vegetation communities, row crops, biofuels, et cetera, would have different kinds of hydraulic roughness. But what you'll see, and we readily acknowledge, is that there's a lot of work that needs to be done on this whole thing about how trees and other types of vegetation impede the flow, and it's critical to this analysis and how these flow corridors work. We're dealing with hydrology that's determined by this entire basin, all the snow melt up in the Rocky Mountains, what happens on the Great Plains, all those things that are similar to what Chris and Tony were talking about in terms of the regional climate. But we're narrowing in on what happens when that water interacts with the floodplain at a much more local level. And the place we're going to be looking at is right down here in our own backyard. So here we are in Columbia. I have Boonville marked here along the river, and also Jefferson City. And the reason is we have long-term stream gauges in both of those places. Working with my colleagues at the Corps of Engineers, the Corps of Engineers has a one-dimensional hydraulic model, on a cross-section by cross-section basis, balances mass and momentum and energy. And they have one of those, so it's a relatively low resolution model, and they have one of those from Boonville down to Jefferson City that they've been using for some planning purposes. And what we've done is we've nested a more high resolution model within that in this area, the model domain showed here down near Hartsburg. And this shows the topography, both of the river and of the floodplain. You can see it's a fairly complex river system, especially the floodplain has a lot of topographic variability associated with that. And so we've done a multidimensional model in this area using bathymetry from the 1990s, photogrammetric observations of the elevations of the floodplain, which are actually quite accurate. The topography and the bathymetry are all gridded at 5 meters, but we have a computational mesh at 20 meters. So every 20 meters along the floodplain and the channel, we're balancing momentum, conservation of mass, and conservation of energy, and developing water surface elevations and velocities. Of course, we went through some calibration processes. I won't spend a lot of time on this, but this is the bottom of the river from upstream to downstream. The red dots, we are calibrating to the Corps of Engineers data. Red dots are from the Corps of Engineers, and this is our calibrated water surface profile for a 5-year flood, which is about 240,000 CFS, or about 7,500 cubic meters per second in this area. So that relationship is pretty good, another pretty good relationship. The important thing about this calibration is, and I think it's similar to climate modeling and modeling natural systems in general, we can calibrate under current conditions and get all our parameters set up correctly. But because we're going to be modeling scenarios that we can't calibrate, we're necessarily stepping off in the deep end when we go into these scenarios. So just keep that in mind when you look at these model results. We've calibrated it today, and we think it's doing okay, but we're going to be looking at scenarios that do not exist. And so we're off into that uncalibrated space. And this is essentially what we're looking at. It's a combination of hydraulic roughness, different kinds of hydraulic roughness up here, and we're using the Manning's N flow resistance, which is a very simple parameterization of this hydraulic flow resistance. And then we're looking at different levee setbacks, going from the levees that existed before the 1993 flood to no levees at all, with a couple of intermediate levee setback scenarios in here. 1,500 meters is about the Pick-Sloan floodway, and 3750 is about halfway in between. And so we're trying to look at that range of scenarios. I'm not going to show you all that today, but looking at the sensitivity along with that. The choice of Manning's End I'll get into more, but to give you an idea, the 0.05 is usually associated with ag, fallow ground or a grass field, and 0.2 is very dense vegetation. So what we do here is we look at these different levee reconfigurations, allows us to look at how that changes surface flow patterns. We are looking at this different range of roughness to look at sensitivity to what those land use changes are. We look at this in terms of both steady flow, which is like a just say here's a discharge and it's moving through this area, as well as an unsteady flow. What happens when you actually route a hydrograph through that? The hydrograph we're using is a 10-year flood that occurred in 2007. We've also been doing some work looking at how patch structure affects the hydraulics on the floodplain, but I won't be talking about that today. The main concepts here are the first one, which seems like a no-brainer, is that if you increase the top width by setting the levees back, you should decrease the flood elevation. Here's a levee here. If we get rid of that levee, the water spreads out, and by continuity of mass, as long as the velocity stays the same, the area has to stay the same and the depth has to decrease. So we get stage reduction. So people say, okay, let's move the levees back. The kicker in here is the velocity can change because of our old friend vegetation, which is of course where the agroforestry issue hooks in. And this is our roughness coefficient we've been talking about here. If that increases, velocity decreases and the depth goes back up. So there's this interaction of the vegetation communities, which turns out to be extremely important in this. So it's not a slam dunk that if you increase the top width by moving those levees back, you're necessarily going to get a commensurate decrease in stage. The other thing we're looking at is the idea of flood attenuation, the idea that if areas are opened up and these floodplains can flood, they'll act sort of like storage reservoirs. So keep the water for some time and be released at a later time. So you can take the peaks off and release it later on. The water's up on the floodplain for a longer period of time. There can be increased evapotranspiration, which can actually change the water balance, and also the opportunity for infiltration into the alluvial aquifer. So this is another thing we're interested in looking at, how much of this can take place, and it's going to relate to how much storage is available on the floodplain, what those floodplain areas are. But as I've been pointing out, this roughness variable is extremely important. Just give you a sense of what this is like. These are some one-year-old willows growing right after the 1993 flood. This is what they look like after about 6 years. There's actually a person back in here holding a surveying rod. When these willows and cottonwoods are at this stage of succession, it is almost like a brick wall to water. Very, very high roughness. And then, as you know, these communities go through themselves thinning through time, go through a successional process, and they get older. And in some ways, they get less complex. But then also things happen like vines and coarse-woody debris. You see them get debris jams and things on the floodplain as well. So this can get very, very complicated. But we do definitely see this variability through time. The way we actually try to calculate what those roughness parameters are is using an equation that relates the vegetation density and a drag coefficient this is the sort of background roughness, and this calculates a composite roughness. And to get to that, we have to get vegetation density, which we can get from basal areas and density of stems. And as it turns out, there was a data set developed from the agroforestry program here, and it's in Thomas Faust's PhD dissertation for 2006, where he had a chronosequence of floodplain forest communities from 0 years to 100 plus years. And we were able to take that data and calculate this composite roughness value down here. And what's interesting is that, like, as sort of intuitive, these very young communities have a high roughness, almost 0.2, as I pointed out earlier, and they decrease through time. So there's an interesting change in these communities, which has implications for a restoration, a passive restoration, that the floodplain roughness is going to change through time and probably decrease. And these numbers are consistent with what's in the literature. I'm not going to talk a lot more about the implications of that roughness changing over time. It's an interesting place that we're going to go in some additional modeling. But just to point out that The roughness numbers I'm giving you, which are the test sensitivity, are within the range of what we're actually calculating for these kinds of floodplain communities. And especially that this high number is not out of the realm of speculation. That is a very high number, actually, but in some, like, for example, some work that's been done on bulrushes, very, very dense bulrushes, numbers of 0.8 have been calculated. But this is a pretty high number for natural floodplains. So let's see what happens with one aspect. Let's get at the stage reduction aspect. I'm going to be showing you a bunch of cross-sections out of this model domain. We're looking downstream. This is where the channel is right here. So this is going across the river this way. And this is the water elevation. And there's a huge amount of vertical exaggeration here because I'm showing you some relatively subtle changes. And here's where the levee was, and actually still is, where the alignment from 1993. And in purple here, I have the water surface elevation. It is not flat. And that's one of the things these multidimensional models do, is they give you a much better idea what's happening in the channel. This is actually some decrease the water surface elevation just downstream of a wing dike, for example, and that is actually captured in the model. The other thing to notice is just how variable the floodplain is. This is exaggerated topography, but it does, these are not plains, these floodplains, and even though those are, fractions of a centimeter sometimes, that has makes a lot of difference to a lot of these floodplain vegetation communities. But now we're going to move the levee back, and this is to that 1,500 meters. And as you can see, we've decreased the water surface elevation as we would expect in the channel, but we've not decreased it everywhere. And that's because there are different flow paths along this floodplain. And so on average, we've actually increased the water surface elevation. Here's an intermediate levee position. Again, we moved it each time. We're moving the water surface elevation down in the main channel, but this water surface elevation is still higher than it was with the levee in the main channel. We remove the levee altogether, then we get a decrease in water surface elevation all the way across the floodplain. Still some variability in it. Now, all of those were with floodplain roughness similar to like a fallow agricultural field, 0.05. If we had those dog-haired thickets of cottonwood and willow, this is where the water surface elevation would be. In other words, it's pushed it right back up. So it's just barely below, in the main channel, just barely below what it was with the levees in place. So to summarize this is the going from the very low roughness to the high roughness, and this is the difference in meters. On average, all of these scenarios increase the water surface elevation, except for low roughness and no levee. So a couple of things to take home about this. One is that on average, these stage changes are small, and they're also positive on average. There is a large amount of variability on the floodplain, and that affects the pathways that water take down through the floodplain, and so how the water surface elevations are actually affected in the flow corridors. Where the stage reduction takes place is really important, because if that stage reduction is small, but it's right against the levee, so the levee's not overtopped into neighboring agricultural field, then it's been very, very successful. So what's important here is to get the idea that looking at it at this scale can really give us a lot of detail about what to expect in terms of flood risk reduction, as well as what sort of velocities and processes will be going on the floodplain. Needless to say, roughness is really important in understanding this whole problem. What about attenuation? This is that 2007 flood routed through our reach. It's about 12 kilometers long. In gray is the upstream hydrograph. In blue is the downstream hydrograph. And actually there's about 6 lines over on top of each other representing roughness from 0.03 to 0.2. They're all on top of each other. There's no big difference between what goes in and what comes out. There's no real change in the peak. In other words, very little attenuation has actually taken place in this flood event. Why is this? Well, it's a relatively small area of the floodplain. It's about 5,000 meters wide and 12 kilometers long. So it's a small area. but it's also a relatively large flood. This is about a 10-year flood in terms of peak, and it's also a relatively long flood. So the flood is large compared to the storage available on the floodplain. What's interesting about this is this area between here on the rising limb of the hydrograph, this deformation in here. And that is an indicator of the flood dynamics that I'm going to talk about now. These are just some snapshots from the two-dimensional models and get an idea what the results are. There are little arrows in here, which are the vectors showing which way the velocity is going. The blue is deep, and the warm colors are shallow. This is when the water just goes up over bank. And what's interesting is that it goes up over bank, and water's flowing in this direction, but it flows up from downstream to upstream as it floods these bottoms. There's some areas here flooding from upstream to downstream, but areas like this and in here you can see that there's water flooding into these areas. So as the water just goes up over bank up till an area like here at about 8,100 cubic meters per second, water's actually being stored on the floodplain. As the water continues to rise, it eventually connects from upstream to downstream. And by the time we're at nearly the peak of this 10-year flood, water is no longer being stored in the floodplain. It's just advecting through, albeit at a slower rate. So this suggests that it's these floods where floodplain storage can make a difference, not necessarily the higher floods. And would suggest that the effective floods might be in this area, which is about the 2 to 5 year flood range. But the 10-year floods, probably not going to be, and 100-year floods, et cetera, probably not going to be affected by floodplain storage. Another interesting result we came up with is the interaction between roughness on the floodplain and what happens in the channel. If restoration isn't just floodplain, it also, well, it's physically related to what's going on in the channel. If the policy goal is to restore the channel as well, this could be an issue. So we'll look at this cross section here. We're looking downstream. Here's where the channel is here, and this is floodplain. In black is a uniform low floodplain roughness. And so what you can see is these are velocities on the floodplain, and they're getting up high, about 0.5 meters per second in places, and then the velocity clearly increases in the main channel. Now we increase the roughness on the floodplain, shown in this green color, so the velocities go down on the floodplain. But what's interesting is the velocities go up. It's interesting and it's not really surprising when you think about it. The velocities go up in the main channel. In other words, the flow resistance on the floodplain is pushing more water into the main channel. So if there's concern about holistic restoration of the channel in the floodplain, this is something that would clearly need to be taken into account. So that's looking at some of the flood control sorts of issues. What we really want to get to eventually is all the other part of the ledger. What sort of positive ecosystem benefits might be taking place in these flow corridors, and eventually try to turn those into something that we can monetize. But right now we're interested in what's happening in terms of nutrient processing, carbon sequestration, habitat quality, et cetera. And we are asserting that they're all a function of water residence time. The longer you can get the water up there, the more of this stuff can take place. And so we're looking at characterizing these residence time distributions. This is one of the model outputs using particle tracking, and it's a method we're using for characterizing these residence times. A couple of things to note here. This is a dynamic wave going through. The water's going up on the floodplain from about a 2-year flood to a 10-year flood, and it cycles through here, and next time it cycles through, I'll catch it. Okay, notice here, water moving upstream, and here, water moving upstream and onto the floodplain. That's some of the dynamics that are taking place during the flooding process we usually don't think about. But notice also how fast the particles move through the main channel. So there's this really a dichotomy of residence times. So we're using the distribution of those particle residence times to talk about connectivity as well as residence time distributions. So for any one of these scenarios, we can look at these particles and look at their population distribution. This is a log scale here, and this is the number of hours that those particles are spending within the model domain. This is actually a high, this is no levee case and high roughness. But to show you what this looks like, this is the residence time distribution for the levees in place. In other words, most everything is moving through very, very quickly. A few places water gets caught up and stays around for a while. Take the levees out, would have low roughness, and that distribution changes a lot. Our mean residence time goes up to 3 hours from 2.3 hours. A little bit higher roughness here, and we've increased the residence time some more. But interesting, when we get up to a roughness of about 0.1, we start to see a reversal of that. We actually decrease the mean residence time. And you can see we're starting to lose some of these residence time particles in this area, and they're moving back into the main channel. So by the time we're at 0.2, the mean residence time is down to 2.5 hours. So the importance here again is that if residence time is a management goal, then you need to work with the size of the flood, the design flood, as well as the vegetation communities to get the right amount of roughness that's going to retain water for the time that's desired. So to summarize, this multidimensional modeling approach provides a systematic way to assess the flood hazard reduction and potentially ecosystem services of floodways. Hydraulic roughness is a critical variable, and depending on what that roughness is and what that geometry is, those vegetation communities can actually increase water stages rather than decrease them, which is a reality that engineers need to take into account when they look at these flow corridors. But we need to understand the roughness of those communities, the patch structure, the age, the evolution over decades, and restoration timescales. We have focused on residence time. We think it's one of those fundamental values of the system we can relate to ecosystem services, but we need to obviously do a lot more work to demonstrate what that linkage is. The residence times reflect these complex flow paths and the effect of varying roughness and the levee setbacks. Thought I would wrap this up by talking about implications to agroforestry. I think the implications, probably a lot of you see what this is. There's opportunities for other kinds of agricultural practices within large floodplains of large rivers. They may be compatible with dynamic floodplains and may be more compatible than some of the conventional agriculture, which is, of course, very susceptible to damage from these intermediate and large-sized floods. Potentially, these flow corridors and different kinds of management of them can result in increases in biomass production, a decrease in flood hazards, and possibly an increase in some of these other ecosystem services like nutrient processing. The critical need, though, as I hope I've established here, is really understanding the details of the interaction between the flow, the geometry of the floodplain, and the hydraulic roughness imparted by the vegetation community. So thank you very much for your time and attention, and I'll be happy to answer questions if there's any time available.
Thank you, Rob. We do have time for a couple of questions.
Yes?
Does the Army Corps of Engineers, pardon me, does the Army Corps of Engineers use you as a partner in deciding what to do, or do they have different priorities entirely?
Our relationship with the Army Corps is interesting. They fund us to do a lot of work. This particular work, they treat us sort of as a crazy neighbor. We think outside the box, and so they use that, but they don't adopt these ideas. We're sort of a sounding board. This kind of research is a sounding board for them. The Corps is working towards doing some feasibility studies of the flow corridors. Right now, what they're really focusing on is there are some pinch points along the Missouri River, especially at bridge crossings, where they have consistent problems with levee breaks. And just from a levee safety point of view, they're finding the justification to move those levees back. There's a lot of politics involved in that. You are changing the potential of private land when you do that, a lot of interaction with levee districts, et cetera. So the Corps moves slowly in that direction. This research is kind of far out as far as implementation by the Corps, but it does, I think, inform some of the thinking.
Thank you.
I hope.
Got a question on levees. Is it good or is it undesirable to have tree vegetation on a levee on the flood side or the river side of a levee? Is it good and bad, and if so, why?
Well, of course, there's been research done here at MU to show that trees are a good thing for levee stability. There's certainly a range of opinion out there. You won't find a levee engineer, or you won't find very many levee engineers who like to have trees on their levees. And the reason for that is dominantly a maintenance one. When you have a tree in a levee, you can't see things like rodents that are burrowing into the levee, which means that you can't plug those holes, etc. On the other side of things, you can see that trees would impart erosional resistance because of the root structure, and they would have some flow resistance as well, as we've shown here, which would decrease the flow of water and in some cases could prevent lateral erosion of a levee. So I've tried to not answer that question as best I can, just to point out that there is certainly a range of opinion on that.
Well, this would be a quick follow-up question since you've been evasive, which I figured you probably would be. Most levee districts hire somebody to kill trees on a levee, supposedly kill them. Most of the guys just cut them down, they sprout back, so they don't really solve that much of a problem. But nevertheless, if they did it right, they'd eliminate trees on a levee. And you seem to point to research that trees are beneficial, and yet the levee boards evidently decide otherwise. If one's better than the other, why don't you do it the right way?
Yeah, and I don't have any direct research that's really addressing how it relates to levee stability, but it is true that standard operating maintenance practice is to remove trees from the levees.
Thanks, Scott. Any other questions? If not, I have a quick question for you, Rob.
Yes.
The roughness concept that you presented, is that being used in designing restoration strategies in the corridor, in the floodplain?
Well, it is by necessity in that all the hydraulic modeling that takes place has a roughness parameter in there. And what's interesting is that most of the time, there's a book actually published by USGS that has pictures in it. So you have pictures of floodplain communities, and you thumb your way through the book and you pick out a picture and you say, oh, that's what my end value is. This is a very simple way to parameterize roughness, and roughness can get very, very complicated. When you think about it, trees bend over. As water goes up, you also might intercept branches. So now you've got different amount of flow resistance depending on the canopy structure or the structure of the tree community and what the understory is like, and then whether you've got coarse woody debris, et cetera. So it can get very, very complicated, and there's a lot of people doing work at the forefront. When you work in the modeling sphere, especially as you get into engineering modeling, there's a lot of emphasis on trying to find a parameterization that is sort of useful and cost effective. So the end value is used all the time. Whether they're coming up with a better number or not is another issue. We've done the calculations on what those dog hair thickets are like, for example, and we've used that in some of the modeling. We've got a paper that's in press right now. One of my colleagues from the Corps is on it, and he's just shaking his head saying 0.2 is really high, because it's not in the book. But I was out on the floodplain in 95 at Lisbon Bottoms, and we were out in a canoe taking velocity measurements along in some of those dog hair thickets, and we just got zeros everywhere we went. I mean, those things are like brick walls. So. Steve.
Okay. Oh. Yeah, okay, we'll entertain one more.
I'm sorry. So in a place like Lisbon Bottoms where there's actually a chute that cuts through, does that kind of change, you know, a lot of the modeling you were showing here was Plowboy Bend, and there's no actual flow, direct flow or channel through that bottom. Do you see sort of changes when there is water being carried through a channel through the bottoms as in addition to the main channel?
Yeah, we've done some of this modeling up at Overton, and there's definitely an interaction between those chutes and what happens in the floodplain. You get more pathways, more opportunities for water to get up and to stay up in the floodplain. At the same time, one of the things many of you probably noticed is that there's no groundwater in this model. and groundwater is an important part of it. The surface water charges the groundwater. You put a chute in, it's like putting a drainage ditch in. It makes the drainage more rapid than if that chute hadn't been there. So you have more opportunity for surface water to get in, but you can also drain the groundwater easier as well. So, thank you very much.